Okay, let's work this, this example. In this problem, we have a car that's coasting along at 110 kilometers per hour, and we want to know how high up some road it goes. The first thing we want to do is get our velocity into normal units, meters per second. And so when you convert 110 kilometers per hour, okay, you need to multiply it by 1,000 to get it in meters per hour, and then divide by 3,600 seconds in an hour, and that gives you 30.6 meters per second. So that's kind of the first step. We need ordinary units here. Okay, now we want to know how high the car just coasts to. And since there's no friction involved, there is no friction, that means mechanical energy is conserved. So initial kinetic plus initial potential energy equals final kinetic plus final potential energy. Okay? All right, so our initial kinetic energy is 1/2 mv initial squared, where v initial is our 30.6 meters per second, plus potential energy, which is mg times the y height. Now we're taking our initial y height as 0, so therefore our initial potential energy is 0. Okay? So therefore this equals final kinetic energy. What's our final kinetic energy? Well, the car comes to a stop out here at its high point. So final kinetic energy is also 0. Okay? So that's 0, and so is that. Our final potential energy is mg times our final y height. Okay? The masses cancel, and we can plug in these numbers now. 1/2 v initial is 30.6 squared equals g, which is 9.8 times our final y height. And that gives a final y height that is 47.8 meters. Okay? So that car coasts 47.8 meters up the road there. Okay, now part B of the problem, slide that over a little bit. Part B of the problem says that, well, the car now goes 22 meters up the slope instead of this 47.8 meters. And the reason for that is friction. And we want to calculate essentially the energy released by friction, the energy lost to friction. And basically, when you lose energy to friction, it goes into thermal energy. So what's going on then is that energy is going to thermal energy. So if thermal energy is allowed to change, our conservation of energy equation becomes this: initial kinetic plus initial potential equals final kinetic plus final potential plus whatever the change in thermal energy is. Okay? Okay, so if that's the case, then we can enter our values here. Kinetic energy is 1/2 mv squared, the initial squared. Initial potential energy, our initial height is 0, so initial potential energy is 0. And that equals our final kinetic energy. Final kinetic energy, the car comes to a stop at our final height. So final kinetic energy is also 0. Final potential energy is mg times the final y height plus our change in thermal energy. Okay? So therefore, delta E is this minus this. Okay? And so we plug these numbers in here. Our change in thermal energy is 1/2 mv squared, mass of the car is 750 kilograms. Initial velocity, again, is our 30.6 squared. Minus mg, m is 750, g is 9.8. Final y height is 22 meters. Okay? So you do that calculation, and our change in thermal energy, or in other words, the energy released by friction, and I'm going to go ahead and erase this just because we need the space here. The number you get when you do that calculation is 189,000 joules. Okay? So there's our energy released by friction. Okay, now part C asks us to calculate what the average force of friction is. Okay, if it's a steady slope at angle 2.5 degrees. So I'm going to have to erase this. So let's go ahead and erase all this stuff here. And we'll save this part because that's going to be important. Okay, so part C then. Okay, now part C, we just found in part B, was the change in thermal energy is 189,000 joules. So therefore, friction did this exact amount of work on the car. Okay, so this is equal then to the work done by friction, which is equal, work again is force times displacement. So force times displacement. Okay? So therefore, the force, friction, is 189,000 divided by the displacement. Now, this is where we have to do a little bit of trig to figure this out. So let's say we have some incline here. Okay, that's a 2.5 degree angle there. Well, here's our distance d. That's how far up the slope the car goes. That's our distance d that the car travels. And friction applies a force opposite the car's motion during that entire path. So what's the height here? Well, the height of this, as we're told in part B, is 22 meters. So therefore, 22 divided by d is the sine of 2.5. Okay? So therefore, d is 22 divided by the sine of 2.5. Okay? And that answer there is 504 meters. Okay? That's the distance along the road that the car travels. So that 504 meters goes in here for D. And this was joules, or Newton meters. So you do that calculation, you find a force that is 375 newtons. Okay, so that's the force of friction on the car as it's traveling up the road. And that friction does work on the car and reduces the height along this road that the car can actually go.